All right, let's take a look at another example dealing with maybe a different type of function than we're used to dealing with. It says consider the function that assigns a number x, that's our input, okay, to the value of x raised to the third power. So you might hear me say x cubed. That deals with geometry with volume, side length times side length times side length. So a lot of times when I see that little exponent of 3, I'll say cubed. But this is going to be our output, right? We're going to put our input in here for x and get a number out. So do you think this function is linear and or not linear, nonlinear? I'm hoping you all agree. Maybe if I'll spell it correctly. Let's go. I could say not linear, but we'll say nonlinear. And when it asks to the explain, we'll just say the exponent isn't 1. I should say 1 or 0, okay, because if it's to the 0 power, remember that is anything to the 0 power is 1. Okay, but that's okay. We'll go exponent isn't 1. Now, just like we've done before in our last example, and many examples before, we're going to take our inputs here and our outputs. We're going to input these numbers into our function and get our outputs. Even though it's not linear right now, are we assuming it's not linear? We're not doing any of the work any differently, okay? So we are going to put x to the third here. So I am going to, and remembering, you can use a calculator, but put this in parentheses, negative 2.5 to the third. Now, you don't have to use the raise to the third button. You could put negative 2.5 times negative 2.5 times negative 2.5, whoops, 2.5, okay? And what you would get, sorry, I have to put it up here, is 15 negative, because there's 3 negative signs there, 15.625, okay? So now we're going to do the same thing for negative 2. Negative 2 to the third, negative 2 times negative 2 times negative 2. That is going to be negative 8. Now notice these are negative when we head to the second power, they're positive. That's because a negative times a negative is a positive. Negative times a negative times a negative is going to be negative. Oops, that's a 3. This is a 3. And that's going to come out to negative 3.375. Okay, so negative 1 to the third power equals negative 1. Negative 0.5 to the third power equals negative 0.125. Okay, and again, I've done this workout already. I typed all these numbers into a calculator. That's how I'm getting these answers. 0 to the third power, 0 times 0 times 0, still 0. Now, 0.5 to the third power, that's going to be really similar to negative 0.5, except this time it's going to be positive. A positive times a positive times a positive, going to be a positive. So we get positive 0.125. 1 to the third, and for some reason I put this in parentheses. You can. You don't have to. 1.5 to the third is 3.375. 2 to the third is 2 times 2 times 2, which is a positive 8. And 2.5 to the third is going to be 15.625. So you're seeing how we have like the same numbers out here. Well, up top it's negative, down here it's positive. Okay, so let's go ahead and graph it now in here. And I'm going to pick a different color. And we're just going to have to guesstimate the stuff. Okay, close approximation to these numbers. So if I start at negative 2.5 to negative 15.625. So here's negative 2.5, left to right first. And here's 15, right? 15 is going to come in between here. So there's 15, and it's about halfway between the 15 and 16. That's why I'm like, we're just going to do our best approximation. Thankfully, negative 2, negative 8, this ordered pair right here, we know how to do that. Negative 2, negative 8. Then we have negative 1.5, again, halfway between, and negative 3.375, that's almost to the 4. Negative 1, negative 1. Be careful. Okay, remember, our scale on the y-axis is going by 2s. 0, 0. Yay, I can get that one. Except I missed 0.5 here, didn't I? Negative 0.5 to negative 1.25. Oh, that's almost to 0. And then we have 0, 0. And then notice here, I have 0.5, 0.125. So here's 0.5 to the right of 0, and then just barely above it. Okay? Approximately. And then we have 1, 1. Remember the 1 comes in here. And then we're going to have 1.5, 3.375. So this is 3 somewhere in here. And then we have, did I miss this one over here too? No, I didn't. Okay. I put this one kind of in the wrong spot. Sorry, guys. It's really not that far off, but I took it as 3.75 and it's 3.375. Sorry, but it's really not that big of a deal. 2.8, thank goodness for those. And 2.5 all the way up here between the 15 and 16. All right, whew, check this out. These are kind of cool functions because they have like greater rate of change here, and then they slow down, and then they go up again. So again, what type of shape is this? And we're just going to say it's a curved shape. Okay, just some type of curve shape, not a straight line like we're used to dealing with. Okay, now let's find some rate of change. Okay, so now for all of these, and I'm going to squeeze them in here. For all of these, we are going to be using the formula m equals the difference, our slope formula, right? The difference in our y's, y2 minus y1, over x2 minus x1. And I'm not going to write that every single time, okay? Just because I tried to squeeze your notes on one page, and so we're going to have to just write it once. I don't think you'd be too upset. All right, so rows 2 and 3. 1, 2, and 3. So these two. So I'm going to have the ordered pairs. Was -2? Yep, that was number 2. Okay, so -2, -8, and I'm just pulling this off the chart, and -1.5, -3.375. Okay? X, Y, X, Y, first point, second point. Okay? And I'm going to plug it into this formula. So my y sub 2 is I get -3.375 minus my y sub 1, -8, over my y sub 2, -1.5, minus my x sub 1, -2. Keep, change, change. Subtracting is the same thing as adding the opposite. Keep, change, change. And this works out to be, just typing into a calculator, -4.625 over, well, no, this is going to be positive up here. I'm sorry. Positive 4.625. Sorry, we'll catch these errors here. Over 0.5. Okay, which equals 9.25. All right, so our first rate of change between rows 2 and 3 works out to be 925. Okay, now it wants us to do between 3 and 4. So this is still 3, and here's 4. -1, -1. Okay, so, whoops. Sorry, I'm squeezing it in here. I need to learn to write smaller now. -1.5, -3.375. And -1, -1. Those just come here off the table. Okay. X, Y, X, Y. Label 1 your first point, label 1 your second point. Plug it into our formula. Okay, this is the formula I keep using. So y2 is -1 minus my y1, which is a -3.375, being very careful not to use lose my negative. And then I have -1 minus -1.5. As always, keep, change, change. Subtracting is the same thing as adding the opposite. Keep, change, change. Okay, and we will get a positive 2.375 over a positive 0.5, which works out to be 4.75. All right, so you can see, because we expect this, it's nonlinear, right? We don't expect our rate of change to be the same. Okay, but I want to show you one more example. It says between rows 8 and 9, and that's going to be these two right here. Okay, 1, 1, and 1.5, 3.75. And 1.5, 3.375. Okay. X, Y, X, Y. All right, using this formula again, sub 1, sub 2. So I'm going to go 3.375 minus 1 over 1.5 minus 1. And I'm going to get 2.375 over just 0.5, right? And when I divide that out, I get 4.75. Now look at that. Do you see how that one, we have the same rate of change, okay? And it's where it falls in the graph, right? They're going up by the same amount, but that's not continuous for the entire graph, for the entire function. So that's why we need to know a lot of things about functions. We need to know about the exponent being something other than 1 or 0. We need to know what the graph looks like, and then some rate of changes. And we can use all of that information to make a decision about being linear or nonlinear, or just having that knowledge of nonlinear functions.